Chapter 12, Basic Electricity. These are the learning objectives. Take a moment and review them. As I mentioned during our lab, electricity flows using these subatomic particles. Protons that you see here are the positive charged ones. The electrons have the negative charge. It's the electron that's in the outer orbits is the one that moves. And this is a picture showing that how that valence electron moves from particle to particle. There's a name for this force that moves it. It is EMF, electromagnetic force. It's measured in voltage. On your meter, it would be you would set your selector switch to the capital V or perhaps the capital E. So 1 volt of electromagnetic motive force is required to send 1 ampere of current through a resistance of 1 ohm. What flows in a circuit is an ampere. This is the old analogy of water and how the force or the gravity of the water and how electric current flow mimics that. This was my explanation of what makes a circuit. A circuit has 3 things: a power source, wires, and a load. What you see is the battery is the power source, and the wires are the lines, and the load is the light bulb. Resistance, which is measured in the symbol omega there, is used to restrict the flow of current. And when it does that, the electric is converted into heat. This is that thing that you all really love, Ohm's law. There are 3 basic formulas. There's a zillion of these variations, but the 3 basic is define for E. In other words, define for voltage, it's amperes times resistance. Define for resistance, it's the voltage divided by the amperes. And to find the amperes, it's the voltage divided by the resistor. Capacitance is the means of holding a charge. It's measured in farads, commonly microfarads. Where do we see capacitance? We see it in capacitors. A capacitor is almost just like a battery. However, a capacitor we use are going to be 2 basic types. One's going to be used to start a motor, called a starting capacitor, and the other's going to be to help the motor improve its turning, improve its power usage, and those are called running capacitors. So never assume a capacitor's charge, because it will hold a charge just like a battery, and so it can give you a nasty shock. Static electricity is, you know what this is. You've all been shocked by static electricity. Just going across the carpet on a winter day in dry weather and then touching the doorknob. Static electricity is electricity that we cannot put to use. However, in that last slide, they were making the point that they are using static electricity to help with air filtration. So as you all know, we use conductors, which are metals that allow for the easy flow of current, and the most common metal that is in use is copper. And we use this for both direct current and alternating current. This is an example of my circuit. This one includes a switch, and this is a series circuit, meaning there's only one path for the electric to go. Alternating current is current that starts in one direction, stops, and reverses and go in the next direction. And this is called, it's measured in how many times it alternates is called frequency. And how many cycles per second is what you hear them refer to as, oh, this unit requires 120 volts alternating current, and it has 60 cycles. So that means one cycle per 60 cycles per second. As I said, conductors are made of metals, and wires are either solid or stranded. Insulators are those things that do not easily conduct electricity. What's in between is called a semiconductor. And so a photocell that's used on an oil burner to prove that the flame is going is an example of a photocell. We have other things that we now are using in our business. The ductless systems have a series of SCRs, silicon controlled rectifiers. And this is what I've been saying. A circuit coming from the word circular. Here's an example of a series circuit where you have three loads that are in a series with a battery as its power source. This is an example of a parallel circuit, again using lights as the load in the circuit, and the battery is your power source. And here's an example of a combination of series and parallel circuits. Every system that you will work on will fall into this category, where there will be a combination of series and parallel circuits. Voltage drop is what occurs, particularly in a series circuit, when it encounters resistance. Some of that voltage that had to force through that resistor will drop. So if it was 120 volts, perhaps after it encounters that resistance, there may only be 100 volts left. Measuring voltage drop. Here is the calculation, the means of doing that. As you can see, voltage drop in a series circuit is called additive. Voltage drop in a parallel circuit is very different. We use parallel circuits for our loads in air conditioning and heating and refrigeration. So our loads, what are our loads? Motors, fans, compressors. Those are wired in parallel. Our safety circuits or sensors are going to be wired in series. Normally our parallel loads are high voltage, and our safety sensor control circuits components are in series. Magnetism. It's important to understand about magnetism because this is going to tell us how our motors are going to operate, what makes them turn. So there's two kinds of magnets, and I think all of you know this. There's the permanent magnet, and then there is the magnets that become magnetized when electric current flows through them. This electromagnetism is important because this is going to be how we induce current from one side of the circuit to another without there being wires connected. Why is that important? Well, the reason why is that you could never get a motor to ever turn if they were wired. So we use that induction, that inducing of that current through there. The strength of an electromagnet is based on these four things: the number of turns that it's going around a core, the strength of the current that we're putting through it, and what the material and the construction and the length of it. I also say this, in which they're not saying here, I'm kind of surprised, it depends on the circular mill, the size of the wire. So heavy wires make up, with few turns, make up weak magnets, and small wires with many turns make up strong electromagnets. When it comes to the core material and construction, the best material is iron. Magnemotive force, MMF, different than electromagnetic force. And here you see an illustration. This is an induced electric field. So the center of the core, what's turning in that wire loop, is being connected with those things that you see are brushes. So that's making an electrical connection. But the energy that's being transferred into that red block, blue block is purely from induction. And in this case, this is a direct current generator. Transformers. We use step-down transformers to take our high voltage and to make it into 24 volts AC, and we use that 24 volts AC for our control circuits and safety circuits. This is what a step-down transformer looks like. The primary is the high voltage side, the secondary is the low voltage side, and you can see the primary has many turns and the secondary has fewer turns if it's a step-down transformer. And they're showing you 100 turns, 50 turns, meaning this step-down transformer is going to be 50% of what it was for the primary voltage, 120 in, 60 volts out. Transformers can go the other way. They can be step up, 120 in, 240 out. And even though they didn't say it, there is a third transformer. It's called an isolation transformer, and you see those things incorporated and used on ships where you can have a ground return.